Uh, yeah, like I said, the XRD theory itself is posed in terms of interplanar spacing. So let's take a quick step back and then look at what the um, crystalline stuff is all about. So what we mean by this regularity is um, a repetitive arrangement of atoms, and the technical term for this is translational periodicity. That is, or sometimes it is also referred to as translational symmetry. So if you have a crystal, it is very easy for you to imagine, right? So you move stuff from um, one place to another, and you get back the original thing. And that is basically what we mean by translational periodicity or translational um, uh, symmetry. By the way, I mean, there is a wrinkle to this story as well, and that is a much more modern development. And there is a set of crystals called quasi-crystals. We'll come to that later. And but that's a complication that we will worry about only a little later. Okay, so let's yeah, these little triangles are my cartoon version of molecules that are sitting at regular spacings in 2 dimensions. And if you just replace all these guys and only look at where they are present, what you get is something which is again depicted in a cartoon form on the right. And then you can see that the gray parallelogram is the fundamental unit, which when translated by a vector A or a vector B or any multiple integral multiples of these, you will generate the entire lattice A. And of course, if you translate the entire lattice by these vectors, then you get back the original lattice, which is again the definition of translational periodicity. All right. So that is just translational periodicity. But the moment you see that it is a parallelogram, you also realize that you get automatically in 2 dimensions a two-fold rotation symmetry as well. Two-fold is a technical term that is used for the n-fold symmetry. Basically means anti-clockwise rotation by 360 divided by n degrees. So it's a 180-degree rotation. It will get back the original lattice, which tells you that this is it arises from translational periodicity only in 2 dimensions. We'll look at the complications in 3 dimensions, but we can get a lot of information, a lot of basics right just by looking at the 2-dimensional lattices. And that is what I want to focus on. Again, I think this is where the book makes a mistake. It introduces, plunges you directly into this 3D business. And in 3D, I mean, it's a bit painful to get the hang of what is going on, and one rarely realizes I mean, the importance of some of the basic things that arise. Right now, we are still in the realm of definitions. We are not doing anything interesting. But the main point here is that any 2D lattice is just a set of points, rather like Rangoli dots that people use in India. And it's a regular pattern of dots. And well, these dots are mathematically sharp, so zero width and all that, but you get the point. And any parallelogram will be able to generate a nice lattice for you. And the moment you have such a lattice, then you also realize that even without doing anything further, for any arbitrary parallelogram which is repeated in space, in 2D space, you get this buy one, get one free kind of deal here. You get two-fold rotation symmetry as well. It comes with the territory, which is nice. But we don't have to stop there. There are special versions of parallelogram for which you will get additional symmetry. All right. So here is the first one. When the, okay, let me just go back quickly. Sorry. Yeah, the lattice obviously is defined by the basis vectors A and B. But you can also think of this as being defined by the absolute values of A and B, the length of these vectors, and the angle between the basis vectors. So when that internal angle here is uh, 90, you get this really nice feature. What you get is a rectangle. You get additional symmetry. What are the new symmetry elements that you get for a rectangle that didn't exist in a parallelogram? Anyone? Somebody has to pipe up and say something. Otherwise, I'm not seeing any hands in this mode. So you will have to tell me.
So probably a reflective symmetry. I mean, that's the only thing that misses from a parallelogram.
Right, right. Now, the think of yeah, it's the reflection, extra reflection plane. The plane that we are talking about is the plane containing A and the Z-axis, and the plane containing B and the Z-axis, the vertical plane. But in 2 dimensions, we don't want to be talking about all these vertical planes and stuff, though that is one good way to make the final transition to 3D crystals, which we will come to later. Right now in 2D, the line, the edges of this rectangle, they act as mirror plane. So you get additional mirrors along A and B, but you also get additional mirrors. Anyone?
Along the diagonals.
No, for a rectangle you won't. For a
Yeah,
square,
that's a square. Sorry.
yeah, for a square you would, and we are coming to that just in a little bit. Yeah. How about through the middle of the rectangle, along the A direction and along the B direction? You're able to see that? It's all 2D. All you need to do is just make a quick drawing and then see for yourself. Okay.
Horizontal and vertical dissection.
What does that come again?
Horizontal and vertical dissections.
That's right. Yeah. So that is basically what those things act as mirror planes. So therefore you get that. What do you mean by a dissection?
No, dissection means slicing from
Okay.
the half.
I don't know. I mean, I'm just trying to clarify what you mean by
Sir, sorry, I missed the question.
No. I mean, we are talking about, I mean, when theta becomes 90, you get additional symmetry elements. And we just discovered that those symmetry elements are in the form of mirror plane, mirrors, reflection about a certain line in 2 dimensions. And we were just looking at what those lines would be. And these lines are basically along the edges of the rectangle, right? And they are also these lines parallel to A and B going through the middle of the rectangle, the center of the rectangle, right? So that's nice. And therefore, I mean, we have rectangular lattice as a special kind of lattice in our list of possible lattices in 2 dimensions. And of course, you can also go to the other extreme where A equals B, and you see 3 different cases. Something that is not special, and where theta is not a special angle like the previous 2 lines. And what you get is a rhombus. Okay. But when you have those special angles, you can now see what is going on. When theta equals 90, what you get is a square. And now square has a lot of symmetry. Name some.
The fourfold rotational symmetry in square.
Right. Both about a lattice point as well as the middle of the square, you get a fourfold rotation. Anything else?
Mhm.
You get mirrors along A and
And the
B as
rest are the
well as
same
mirrors
as
parallel
rectangle
to A and B through the
and,
center. Yeah.
and along the diagonals, as Irish has
Yes.
said.
So you get a lot more symmetry when this condition is satisfied, and therefore this qualifies as a special case. And so that also goes into our list of possible lattices in 2D. And of course, when theta equals 120, what you get is a hexagon, and that is again a beautiful structure. So you get, what are the symmetries that you get for a hexagon? Remember, it is still a parallelogram. The parallelogram, when you place it with this translational periodicity, you can think of it as a hexagonal symmetry. So the word hexagonal here refers to the symmetry, which is sixfold. That just comes out because this angle is special, right? What are the other symmetries that you get? Sixfold is straightforward. What are the other symmetries that you get?
You have reflective symmetry along the uh, diagonals as well as the
Okay,
lines that go through the middle of the opposite
right,
sides.
right. And so sixfold symmetry, along with these special features, these mirror planes, mirror lines, reflection lines, reflection symmetry lines along the diagonals. That again explains the special nature of this hexagon. By the way, what are the extra symmetry elements that a rhombus has as opposed to a parallelogram, a generic parallelogram, non-special parallelogram?
Along the diagonals here.
Right. And where have we seen this? It only has only twofold symmetry. Where have we seen this twofold symmetry with two mirror reflection lines which are perpendicular to one another? Where have we seen this?
In rectangles as well.
Yeah. So rhombus is a special kind of rectangle, and that is why, I mean, you can either think of this rhombus as a special thing by itself. I mean, it is not rectangle though, right? It is not just a simple rectangle. So that is what you see in the next one that I took from Wikipedia. So rectangle, there are two kinds, right? So the first one is above. By the way, let's start with a simple parallelogram here. A, B, they are different, and the theta is non-special, and that's what you start with. And now you go to the second column where there are two different kinds of rectangles that have been drawn. And in the first one, in 2, in the figure numbered 2, you get a simple rectangle. And the figure numbered 3 is a centered rectangle, which actually came from the rhombus here. You see the rhombus that has also been drawn there in figure 3. And of course, figure 4 gives you the unit cell as well as the location of the lattice points. And since the internal angle between A and B is 120, you can now see the hexagonal pattern and the emergence of a sixfold symmetry. The last one, of course, is the square one with fourfold symmetry and associated mirror planes and so on. So we now have, I mean, through in about 10 minutes or so, or maybe 15 minutes, we went through the basics of these things and the basics of how one can get a periodic arrangement of dots. And based on the symmetry, we are able to classify them into 5 different kinds of Bravais lattices in 2 dimensions, which I think is pretty nice. So you have them all here. See if you can think of something that is missing here. And this gives us the foundation to now switch our focus to 3D lattices. By the way, I mean, 2D lattices are sort of interesting these days because, I mean, there are all kinds of 2D materials that people have made. And at the same time, I mean, they're also fairly easy to understand the crystalline nature of these things. What is interesting in these 2D materials like graphene and other kinds of things that people are trying to make and study is the kind of defects that one can form in these 2D structures. We haven't looked at defects yet, and those defects have certain intrinsic properties, and people are trying to figure out what those defects are, characterize them fully, but more importantly, what one can do with those defects to exploit them and use them in some meaningful way. That's why it's all in the realm of research and not quite in the textbook. But anyway, so I think we can all feel happy about being able to generate all 5, the exhaustive set of 5 Ravel lattices in 2D. Now we are just going to fudge things a bit and say the same concept translate quite nicely into 3D as well. So in 3D, you have A, B, and C. Instead of a parallelogram, what you have is a parallelepiped. And so to characterize it fully, you need A, B, and C. And you need the angles between any 2 of them. So they are referred to as alpha, beta, and gamma. And depending on, again, the generic parallelepiped would not have any symmetry other than the trivial one of one-fold symmetry, which is basically rotating the damn thing about by 360 degrees about any axis, not any axis. You have to be careful. Yeah, I would think so. You get back the original lattice, so it is just one-fold symmetry. That's it. Nothing else. There is one other symmetry that you would get, which is not present in 2D. In 3D, you get something called inversion symmetry. Inversion symmetry is basically you take a point and with respect to the origin, and you invert it through the origin. So if you take a position at let us say x, y, z, then the point opposite at the other end, minus x, minus y, minus z, then if you do this operation for all the points and if you recover the original lattice, then it is supposed to have this inversion symmetry. That's it for a generic non-special parallelepiped. That is the only symmetry that is possible. But now you can imagine the kinds of possibilities that you can get when you have special values for A, B, and C, and special values for alpha, beta, and gamma. And of course, the one that we would be spending some time on is a special situation where A, B, and C are all the same, and alpha, beta, gamma are all the same and 90 degrees. And what you end up with is a cube. So we'll spend some time on the cubic lattices. Fortunately, lots of elements have the structure. So because of that, I mean, there's not some fairy tale that we are peddling here. So it actually has some relevance to real stuff, but at the level of elements. And so we'll spend some time on 3D lattices and then 3D crystals, especially with a special focus on the cubic kind in the next. Okay, so I'm going to stop this, stop sharing this screen, and we are back. Okay, any questions in the next 2-3 minutes or so? I'm sorry I could not send you any videos of these presentations, but I will try to do better in the next class. Anything that you want to ask now before we sort of call it a day?
Why do you say that 2D structures don't have inversion symmetry?
It's a trivial thing. I mean, it's a combination of no, it's just rotation by 180 degrees.
Yeah, so it's just one improper rotation, right? And
you're already
2Ds.
talking about, yeah, it's already embedded in an existing thing. Remember, we were always talking about new symmetries that emerge in special lattices. So yeah, in 2D, I mean, there is no inversion, right? It is just trivial. It is just 2D, I mean, two-dimensional, two-fold rotation, which we have already seen. No?
I mean, just because it exists everywhere doesn't mean you cannot classify it.
Maybe
Even
maybe,
identity exists everywhere. You
yeah,
do say
maybe,
that identity exists.
yeah, I understand. I understand what you're saying. There is possibly no. What I mean is, it already exists by another name, and I don't think it brings anything new to the table. So if you, for example, if you destroy one, you destroy the other as well. One of the ways in which you can destroy it is by placing a non-symmetric molecule at every point, right?
Yeah, sure. If you want to say that two-fold rotations and inversion are the same or one and the same, then I guess yeah,
They're
that's fine.
identical, right?
Yeah.
They are identical. So that is why we are not sort of pretty hung up on this inversion symmetry in 2D. That is, if one exists, the other exists, and if one doesn't exist, the other also doesn't exist. So therefore, I mean, yeah, I've rarely thought about it, but since you asked me, I think this would be my answer. But yeah, people normally don't talk about inversion symmetry in 2D lattices. Okay, so the punchline for the next class is that there will be some 14 different Bravais lattices. We will just quickly go through them. I think the fundamental basic principles are done now. And so the same thing extends to 3D. And because the number of variables is much higher, you get a much higher kinds of lattices. 14 of them in all, and they belong to 7 different symmetry classes. And we'll look at them one after another. And it is difficult to create another lattice which does not belong to any one of these 14. So it's an exhaustive set. Yeah, Himanshu.
Sir, can you explain the rhombus and rectangle relation once again?
Just go back to that Wikipedia image that I presented, no? So if you look at the rhombus there, figure number 3, I don't want to display it again, but figure number 3. You look at the rhombus and how one can construct a rectangle out of it, but it is not a simple rectangle. It has a point at the center, so it is not a simple brick. It is a, shall we say, it's a decorated brick. It has something at the center. The same point. Both the point at the center and the point at the corner, they are equivalent. That means if you move the entire thing by that distance, you would get back the original lattice as well. So it is referred to as rectangular symmetry, and I wanted you to see what that rectangular symmetry is all about. By the way, the same idea translates to body-centered cubic and face-centered cubic as well, which will come later in the next class actually. So that's the idea. So you already get the idea behind where a centered lattice is listed as one of the basic lattices. You can still think in terms of a rhombus, but when you look at the rhombus drawn the conventional way, you don't see the clearly. So which is why, I mean, the rectangle brings out that symmetry very clearly. So that's why, I mean, everybody prefers the centered rectangle as the name rather than the rhombus. Yeah, one more raised hand. Deb Burma.
Hello, sir.
Yeah.
So you just asked to remind you of 2 things, like the X-ray diffraction of amorphous substances, and you're also supposed to send a video
right
at the end of this session.
Apple video.
Yeah.
By the way, if you have some time, and if you want to get an experience of I mean, this XRD business from one of the experts, presented in a very, very nice way. It was a popular lecture at the Royal Society. Stephen Curry is really, really nice. Look, most materials people work with crystal structures. He actually, I mean, makes fun of materials people along the way. That is a subtext. We deal with much simpler structures. And whereas biologists deal with horribly complicated things, including the stuff about ribosomes. I mean, ribosome, he actually shows a model of that molecule. It has nearly 500,000 atoms. And it's an amazing lecture. Worth spending 45 minutes of your time, 45 minutes to an hour of your time. And there is really nothing better than getting a popular lecture from an excellent speaker. You also get a very good sense of the kinds of difficulties that people faced. All said and done, it took more than a century, not a century, about 80 years before, I mean, a complicated mess like the ribosome, its structure could be solved. So take a look. I think it's one of the best videos out there. Okay, we'll stop here, and I'll send you the link to the Apple video. Amorphous stuff, we'll come to that towards the end of not this module, this structure and XRDM and stuff like that. I think I've already given a quick and dirty answer already. Yeah, one more raised hand, Chinmay. By the way, if you guys have another class to go to, you're welcome to leave. So no issues. So shall we take up these questions in the chat box, Chinmay? I think it's not fair for us to keep going on. All right. See you all Monday. In between, I'll try to send you A, some home assignment questions, and B, the video for the next 2 sessions. All right. See you all next week.